Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be exploring the vertex of a parabola. In particular, we're going to be examining how to identify the vertex of a given quadratic function. Additionally, we're going to be looking at how to represent a quadratic function, not necessarily in standard form, but in this new form that we're going to title the vertex formula. And of course, then we're going to apply this to solve application and modeling problems. Now first we need to define what is the vertex form and how does this form differ from something that we've worked with in the past. So we're going to define this as, say you're given a quadratic function. And remember, quadratic functions are of the form f of x equaling ax squared plus bx plus c. So say you're given a quadratic function, f of x equaling ax squared plus bx plus c. That was standard form. Standard form. We can represent this function as a quadratic in vertex form. Now, vertex form is just another way of representing a quadratic function. We normally would write it in standard form. That's the form that we factor things down in. That's the form we've always worked with. What we have when we talk about vertex form is a function written in the form f of x equaling a times x minus h squared plus k. This is not something new to us. This is something that we've seen before when we explored how changing around a particular function also can manipulate the graph. If we remind ourselves, h here controlled the horizontal shift, k here controlled the vertical shift, how much we went up or down, and then a was the dilation factor, or the scale factor. A controlled how wide or how thin the parabola was. It also controlled the orientation. Was it facing up or was it facing down? So altogether, the A, the H, and the K all pretty much changed around the graphs that we would work with. Now, again, this format, this way of writing a quadratic function is the same thing as the standard form. It's just a different way of looking at it. Why is this important to us? Well, vertex form is actually one of the nicest forms to look at a quadratic function and to examine a quadratic function. The reason being, we know where the vertex is. If I had something in standard form, I don't really know off the top of my head what the vertex is. But if I have something in vertex form, something in this new format, I know that the vertex is going to be at the point HK. The vertex is told to me because H says you start at the origin and move left or right over this many units. And what K says, if you start at the origin, move up or down this many units. So I know where I took the parent function and where I moved it to. I can't really see that in standard form, okay? Vertex form is the one that tells me that. So that's why it's actually going to be very helpful to us going forward when we do these application problems. Now, one thing you might be saying to yourself is, okay, that's really awesome if you can take this quadratic and put it into vertex form. But how do you do that, right? What's the method for that? How do you even find what the vertex is? So let's start with that question. How do we find what the vertex is of a standard form quadratic? So the vertex formula is a way of finding the vertex from a standard quadratic. So let's write that down. A way of finding the vertex of a standard form quadratic function. So if you had a standard form quadratic function, the formula I'm about to show you will tell you how to find the vertex. Remind yourself that standard form here means ax squared plus bx plus c. Okay? A, b, and c, those are just the coefficients and the numbers that you're working with. So if you want to find the vertex, remember the vertex is a coordinate point. It's some point xy. So if you want to find that, here's how you do it. To find the x-coordinate, to find how far over left or right you are, you need to take negative b and divide it by 2a. Take a look at that for a second. You have to take negative b and you have to divide it by 2a. Now that negative b over 2a, that tells you what the x-coordinate is for the vertex. To find the y-coordinate, to figure out how far up or down you go, all you have to do is plug that value in. Whatever you get for that negative b over 2a, you have to plug that into the function, the standard form, and see what you get for the y value. So let's try this, for example. Let's just try this. Let me clear some space here. And let's go ahead and do an example where we can show how these values are working. So I'm going to leave the formula listed down below, but let's take the function f of x equals x squared minus 2x plus 3. And I'm going to change colors here. So this is in standard form, okay? The first thing we would say is, okay, well, how do I find the vertex? Well, to find the x value, you need to say, okay, well, I need to take negative b and divide it by 2 times the a value. A here is a 1. B here is negative 2. Notice I'm including the sign. And C here is 3. Not that we need it. All right, let's find the x value of the vertex. That's negative 2 divided by 2 times a, which is 1. So that's just going to be negative 2 is positive 2 divided by 2. And 2 divided by 2 is just 1. So that's the x-coordinate. That is what the first value of the vertex is going to be. So as a coordinate point, x is going to be 1. But what's the y value going to be? Well, hopefully you're saying, well, I know what the function is. So if I know what x is, I can immediately figure out what y is. All we have to do is just plug it in. So to figure out what the y is, just plug it into the function. Figure out what f of 1 is. So we're going to take 1 and square it, minus 2 times 1, plus 3. Well, 1 squared is just 1, and 2 times 1 is just a 2. So 1 minus 2 is negative 1. Negative 1 plus 3 is just 2. So there's my vertex, 1 and 2. I now know this is where my parabola is centered at. So this format right here, this form for figuring out what the vertex is, lets you know where you've centered your parabola using the standard form, okay? Remember, standard form doesn't really tell us anything about the graph. Not off the top of our heads, really. Just looking at it, I can't really tell from 1x squared minus 2x plus 3 that the vertex is 1 comma 2? I can't really tell that. So what this formula does is it helps me identify what that vertex is. Make sure you're comfortable with this idea because it's going to be very central in our work of algebra to figure out what in fact the vertex is. Now, let's take it another step further. This is fine for figuring out what the vertex is given a standard form quadratic. But what if I really want to work with this vertex form? Is there a way that I can go from the standard to the vertex form without having to do all this formula stuff? And in fact, yes, there is. Let's take a look at this example right here. X squared minus 4x plus 7. This is a standard form quadratic, and let's make it a function. Let's say f of x equals all of this. Now what we want to do is I want to convert this into the vertex form. I want to turn this into something that has f of x equaling x minus h squared plus k. What I'd like you to do is pause the video for a minute, and I want you to try to think, how can I turn this form into this form? I'll let you know you do know a method for doing this. You just got to try to think, which method is it? Remember, we are altering the form of a quadratic. Think back to work that we've done in the past with quadratic functions. When have you ever altered the form of a quadratic where you end up with a value squared? Take a minute, pause the video, and try to think to yourself, how might you go about changing these forms? All right, well, hopefully you had some time to think this through, and hopefully the idea came to you. The central technique that we're going to use here is completing the square. Remember, when we would do completing the square, we ended up in this form where we had a certain quantity squared plus or minus another value. Let's remind ourselves about how that works. So let me clear some space here. We usually would do this when it was 0 equaling x squared minus 4x plus 7. But we can go ahead and use the function symbol. We'll just pretend it's like a 0. What we would do first is we would move the number over. We would move the c value over. So over here we would have the f of x minus 7 equals x squared minus 4x. Then what we would do is we would take that value of b, which was negative 4, and we would divide it by 2 and square it. Remember, that was some side work that we would do. So we take negative 4 divided by 2, that's negative 2, and we would square it. That would be 4. That value that we figured out is what we would add to both sides. So let's add a 4 to both sides here. So we have the function is equal, the function minus 3 is equal to x squared minus 4x plus 4. Remember, these are like terms and they do combine to negative 3. So the next thing that we had to do was attempt to factor this down. The whole point of completing the square was to try to factor down a polynomial that couldn't be factored. So we can factor this down so that the right-hand side becomes x minus 2 squared. And now all we have to do is add the 3 back over. And here we go. F of x is equal to x minus 2 squared plus 3. We have just taken the standard form, the thing we're very used to working with, and we've converted it to vertex form. These two forms are exactly the same. These are the exact same functions. There is nothing different between the two of them. They're just written in different ways. Now, why is this method nicer? Well, one of the things is I know what the graph is going to look like. I know that the vertex is 2 and 3. And I know that the scale factor, the dilation, is a 1. So this is really going to look like the standard parent function, but all that we've done is moved it over 2 units to the right and 3 units up. Please remember, a lot of times people get confused by the fact that this was a negative 2. They say, should we move it over to the left 2? No. Keep in mind, whenever we would subtract values, it moved it to the from x, it moved it to the right. And whenever we added values, it moved it to the left. If you need, go back into my Desmos examples and take a look at how those functions were working. What I'd like to do now is try another example of this, okay? Let's try another example, but this time I want you to, on your own, try to complete the square to get the quadratic into vertex form. All right, let's go ahead and try this example where we have f of x equaling 2x squared plus 12x minus 5. Now you can go ahead and try to factor this like normal. You can go ahead and try to use the vertex formula, the negative b over 2a, and that's fine. But what I want us to do is get in this habit of completing the square, where we go ahead and alter the quadratic form, the standard form of the quadratic, into the vertex form. So pause the video, take a couple minutes, and give this a try. Now, before we get to the answer, I want to remind you to please make sure that first, what you have to do before you complete the square is make sure that your leading coefficient is a 1. Here, notice that it's a 2. And what was that trick that we had for getting rid of that 2 and turning it into a 1? Well, we would just divide both sides by 2. That would turn our leading coefficient into a 1. So you should end up with a x squared plus 6x minus 5 over 2. Now you'll notice that on the left-hand side, I wrote f of x divided by 2. You don't have to do that, okay? You could just leave it. And some of you might find it helpful to just start by saying, instead of f of x, let me turn that to a 0. And then start from there, where you have x squared plus 6x minus 5 over 2. And just work from that aspect, where you imagine that f of x is 0, okay? Just make sure when you get to your final answer, you put the f of x back in, okay? All right, pause the video again, take a couple more minutes to adjust your problem if you didn't start this way, and let's see where we end up with. All right, let's take a look here. You can see that I used this format where I kept the f of x symbol, and I kept it divided by 2. You don't have to have done that. You could have just made it 0, and you would have ended up right here with a 0 equaling the x plus 3 squared minus 23 over 2. And that's totally fine. But let's take a look and let's see what I did by keeping the symbol there. First off, I added the 5 over 2 to both sides because that's the number value, that's the constant that we have to add over. So I moved that over. Then I took the middle number, which was 6, the b term, I divided it by 2 and squared it. Well, 6 divided by 2 is 3, and 3 squared is a 9. So that's what I added to both sides. Remember, what you got to do to one side, you have to do to the other. So I've added 9 to both sides, and 5 halves and 9 made 23 over 2. I'm just leaving that as an improper fraction. Nothing wrong with that. But we'll notice that the right-hand side could now be factored. It could be factored to x plus 3 squared. So it's x plus 3 times x plus 3. With that solved for now, I could move the 23 over 2 back over to the other side. So I subtracted it over, and there we go. Now, if you didn't write the symbol of f of x over 2 here, you would just have 0 equaling this, right? Notice that, all right, this is okay, but keep in mind, what did we do to start with? We had a leading coefficient of a 2. We had divided that on both sides. So we should end up with another leading coefficient of 2 here. We should remultiply that back in. So let's go ahead and see what happens when I multiply both sides by 2. Well, this side, 2 times f of x over 2, whatever that means, will just be f of x. And then when I distribute a 2 through, let's see, let me clear some space here. We should end up with a 2 times x plus 3 squared, and then minus 23 over 2 times 2 is just 23. Even if you convert it back, if this 2 is 0, you're going to need to make sure at the end you remultiply everything by 2. The reason being is because otherwise you wouldn't end up with the exact same function that you're working with, okay? And you might say to yourself, how do I know that these functions are in fact the same thing? What's to say that they are? Well, why don't we take a look and why don't we work backwards to show that this is in fact the same thing as the original function? All right, the question was, how do I know that this function satisfied the original function? How do I know that they were both the exact same functions? Well, all we need to do is really just simplify this. So let's go ahead and let's start by figuring out what this x plus 3 squared is. So that's 2 times, well, x plus 3 times x plus 3, if I use the box method for that, I would end up with an x squared, a 3x, another 3x, and a 9. So that was an x squared plus 6x plus 9 minus 23. If I distribute the 2 through, I get 2x squared plus 12x plus 18 minus 23. And if I went to combine the like terms, we'd end up with a 2x squared plus a 12x minus 5. So we do in fact get the exact same function back. We wouldn't have gotten that if we didn't remultiply by a 2. So hopefully you're getting down this process of how we can convert from quadratic to vertex, and hopefully you've been seeing how we can go back from vertex into the standard form of a quadratic, I should say. It's really just completing the square and making sure you're being careful with your notation, okay? What I'd like us to do right now is try an application problem. Let's take a look at a very common application problem called vertical motion. Let's read through this problem. Vertical motion is the motion of an object being launched vertically in the air. Okay, that makes sense. The height of an object that has been launched vertically over time can be modeled by this function. H of t is equaling negative 16t squared plus v sub 0t plus 6. This v sub 0 is just the initial velocity of the object. And you can think of velocity, let's call it speed, okay? Velocity would be something like meters per second or feet per second or miles per hour, something like that, okay? Sometimes we call this v sub 0. Sometimes we call that v naught, just as another vocab term. So right away we have a function that describes the height over time of an object. We know that v naught is the initial velocity, and this s here, this s value, is the initial height of the object that it was launched from. And t is the time since the object's been launched. And h of t is the height. So what do I need to figure out what the height of the object is? I guess I'm going to ask myself that question first. How do I figure out what h of t is? what information do I need to get at h of t? Well, I need the v sub 0, the initial velocity. I also need to know the initial height that we launched the object from, and I might need to also be working with the time. So let's go ahead and let's read about what this specific problem says for us. Mr. Linford wants his class to use this equation, or this function I should say, to model the height of an object over time to observe how it changes. So he decides to launch a G.I. Joe model rocket. This is really just an excuse for me to launch a model rocket. In particular, Mr. Linford wants to know the maximum height of the rocket, because the higher up, the better, right? So the rocket is launched from the ground with an initial velocity of 48 feet per second. That's pretty fast. What is the equation of the rocket's height over time, and what is the maximum height of the rocket? So let's try to get a picture of what's going on here. Okay, here we can see a very crudely drawn model rocket, and we are launching this rocket into the air. Notice that the rocket starts on the ground. We're launching it from the ground. And what's going to happen? It's going to shoot up in the air, it's going to go up and up and up, and what happens? Once it reaches its maximum height, it's going to fall back down. And it falls down, usually it tips over and falls nose down, and it would land on the grass, probably right about the same spot that it launched from, unless the wind blew it over a little bit, but fairly close. We would land to the initial spot. So let's try to understand some of the given information here. The rocket is launched from the ground, and it lands on the ground. What is the initial height then of the rocket? Remember, S here is something that we need to figure out because we need to write the equation for this situation. We need to write an h of t equaling negative 16 t squared plus this v sub 0 t plus s. Well, one of the things we have to figure out is what is the initial height s? And hopefully you're saying, well, that initial height is just 0 because you're launching it from the ground. How high up in the air is the ground? Well, it's 0 feet. So I guess you could write plus 0 here, but you don't really need that. So we don't need to worry about the initial height s. We haven't launched it from high up in the air or anything. We're launching it from the ground, and it's going to land on the ground, so we're good. The other information that we need is the initial velocity. What is that v naught, or that v sub 0? How fast was the object initially launched? That's going to affect our height. Keep in mind, if I launch this rocket, I don't know, 10 feet per second, it's not going to go as high as if I launched it 30 feet per second, would it? Because the faster I launch it from the get-go, the higher up it's going to go. Well, we know from the problem that the initial speed of the rocket, its initial velocity, is 48 feet per second. So I know that my function, h of t, is going to be negative 16 t squared plus 48 times t. I don't need to know what t is because that's just my variable, right? And h of t is the height. So the variable time is going to affect the height. Because let's say after 1 second, we might be at this spot. And after 3 seconds, we might be here. But after 7 seconds, we might be here, etc. So really, all that we're saying here is write a function. Well, you know the form of the function because we were given that. So we took all the initial conditions. We knew its speed. We knew its initial height. So we could write this function that models the height over time. Now the big question is, What is the maximum height of the rocket? How high up does that rocket get? Take a minute. Think to yourselves. You know what the function is. You know how to describe the height. You can calculate the height of the rocket for any given second. So try to use this function to figure out what this maximum height is. All right, well, hopefully you had some time to work this through. One thing that you should keep in mind is recognize that this function we're working with is a quadratic. If you look at its graph, you would see that it basically fits the form of a parabola. We can describe over time what happens to the height. Over time, the rocket starts by going up pretty quickly, and then it starts to slow down, and then once it reaches the top of its height, it starts to come back down. And it slowly, over time, will start decreasing, and then it'll really pick up speed, right? So when the rocket gets up way up in the air, it slowly starts coming back down, but then it picks up speed, and it rapidly comes back down really fast. So our question is, if this graph models the height for time, what is the maximum height, that value? Hopefully you're noticing that the maximum height here is the vertex to this parabola. So you should be saying to yourself, well, what's the vertex of that parabola? What's that height value? Well, there's a couple ways of going about doing this. We could go ahead and try to complete the square, but you know what? We've had some practice in that already. Why don't we use the vertex formula, the negative b over 2a business? So let's figure out what this coordinate point is here. First, let's figure out what x is. X is negative b over 2a. Well, let's plug some values in. Negative b here, well, b is 48, so that's negative 48 divided by 2 times negative 16. So what's that going to be? Negative 48 divided by 2 times negative 16 is negative 32. And if we divide 48 and 32, we get 1.5. So x here is 1.5 seconds. That means it takes 1.5 seconds for the rocket to reach its maximum height. So that was moving pretty fast. We shot it up into the air, and after 1.5 seconds in the air, it's going to stop and then start coming back down. So we know what x is. 1.5 seconds. But here's the trouble. That's not what the problem's asking. The problem's asking what's the max height. All I've done is I've figured out what the time it takes to reach the max height. Well, now hold on a second. If I know what x is, can I figure out what the output is? All that we have to do is now plug this value in. Go ahead and plug in 1.5 for the function, and we'll see what we get. Negative 16 times 1.5 squared, and then we're going to add 48 times the 1.5. And I'm just going to check in my calculator. I'm going to take 1.5 and square it. I'm going to multiply that by negative 16, and I'm going to add whatever 48 times the 1.5 is going to be. And that turns out to just be 36. So this point right here, this maximum coordinate point is 1.5 and 36. What this tells us is that at 1.5 seconds into its flight, the rocket is 36 feet in the air. That's the maximum height, okay? Because we already said that we know that the maximum height is going to occur at 1.5 seconds. So just plug it in. That's the beauty of this function. It tells you what the height is given the time. Now, I'm sure some of you are probably already thinking, does this really work exactly? Well, no, there's some error prone to this. One of the things that this function doesn't take into consideration is the air resistance. There, in fact, would be air resistance that would really slow the rocket down. And there would probably be some wind that gets affecting us. The wind could be blowing around the rocket. It could be slowing it down as it comes down. It might be accelerating it. We don't know for certain, okay? So we're really just taking this into consideration, assuming that there's no air resistance and the wind isn't really affecting it. We're just trying to assume some very general concepts about it. Now let's go ahead and take a look at how this idea of maximum height can be changed if we manipulate how we launch the rocket. In this problem, Mr. Linford wants the rocket to go higher. So what we're going to do is we're going to launch the rocket from the top of a 288-foot high building. So let's try to get a picture of that. We have this building, and let's say this is the ground down here. And so, all right, here's Mr. Linford, and he has his rocket. And he's going to launch the rocket, and it's going to go up and up and up and up, and then it's going to come down. But this time, obviously, it's going to go down and land on the ground. What we can say is, how does that affect the maximum height of the rocket? And how does that affect the equation in general? Because in the previous problem, we were starting on the ground, the rocket went up into the air, and then it came back down, and it landed at the same spot. Here, we have a different situation. So keep in mind that the function format is negative 16 t squared plus v sub 0 t plus s. Well, we still have the same rocket, and that rocket can launch 48 feet per second. So we know what the initial velocity is. Okay, we know it's going up in the air 48 feet per second. This time, however, our s is going to be different. We are not launching it from the ground. We're, in fact, 288 feet up in the air. You might be saying to yourself, well, how does that affect our problem? Let's remind ourselves, in the previous situation, when I launched the rocket from the ground, the maximum height was 36 feet. Now when I launch the rocket from the top of the building, it's going to go up 36 feet. So would you say that the rocket's height, this whole distance right here, is 36 feet? No. You're going to say it's 36 feet plus 288. How high up from the ground would the rocket's max height be? Well, it would be 288 feet up from the ground, because that's how high the building is. And then you've added the 36 feet in the air it traveled. So really, the max height of the rocket now is 324 feet. This is telling us that, yeah, if you start higher up in the air, your rocket's going to go higher up in the air, right? You can pretend like you're launching it from the ground, and that would tell you, you can figure out how high up in the air it is from where you launched it. But keep in mind, if you're way high up, say you're up on a mountain or on the top of a building or somewhere, or maybe you're just holding it up in the air 5 or 6 feet, that's going to affect the initial height because you're telling it to start up even higher. You're giving it almost a head start, okay? Hopefully these problems are making sense to you. Hopefully you're seeing how, one, you can switch between standard and vertex form, and hopefully you're able to not only work with vertex form, but with the vertex formula to get a better understanding of quadratics, get an understanding of how to identify what the vertex is and what it tells us for these application problems. If you have any questions, please let me know. My email is klinford, that's KLINFORD, at wccnet.edu. Let me know if you have any questions or comments, or if you need me to go over anything in more detail, please let me know. And until next time, take care.